friend of mine many years ago, a programmer said to me, "Oh, you should learn more Rust. It's actually fun again to write code." I was like, "Oh, nah, it's fine. I'll accept." And I should have taken his advice, because actually writing code in Rust is fun. You know you've made it when you look at some code. You're like, "Who wrote this? This is horrible stuff." And you look back in the log and you realize that was you. So that's when you know you've been around a little too long. One of my managers at IBM for years, he would come to me and say, "Hey, is Linux done yet?" And I was like, no. And I finally realized I should say, "Hey, it will be done when you stop making new hardware." The fact that there's 6 billion Android devices out there running Linux is pretty amazing.
First, can you tell me a little bit about yourself? How did you start programming? So that we can kind of place you a little bit. When was it? Where was it? How did you learn how to program? All the stuff like that.
I programmed it really young. I'm in my 50s now. I started when, 12 or 13. My friends said they never saw me the summer between 5th and 6th grade. And I think that's when I learned how to program. My parents bought an old TRS-80, or it wasn't old at the time, new. And I learned how to program in BASIC and assembly language and went from there. And I messed around with it on my own, went to university, finally graduated university after many years in computer science because I didn't know what else to do. And I got a job and I worked in the embedded world. I did embedded stuff. I did printers, I did barcode scanners and things like that. I come from the embedded development. I started off doing serial ports as my first paid job in the early 90s, and I'm still doing serial ports today because serial ports are still around. Same chips, it's just never going away.
Okay. Why did you say after many years have you graduated? What was happening?
It took me 7 years
to
graduate. I was kind of kicked out of university for a while.
Okay.
It took me a long time to get through. I met she's my wife, and she's like, "What are you doing? You could just go back and finish up your degree and just do that." I'm like, "Okay, yeah, I guess I should." It's a long story. The way the universities worked, I was going to university in Florida. I lived in Florida. I grew up there. You had to, after a couple of years, you had to apply to your your upper college. And if you didn't have good enough grades or whatnot, you couldn't get in. And it turns out I didn't get good enough grades in my non-computer science classes to get in. So, which was very common. It turned out 1/3 of the incoming freshmen never graduated. So it was a way that the universities could get people coming in from community colleges into their stuff. They've now changed it. It isn't as bad, but turns out I was one of the 1/3 of people that were kicked out. But
okay.
A lot of us came back. I eventually did get my degree, so all's good.
Okay, nice. So how and when did you join the Linux Foundation and work on Linux in general?
So I started working on Linux at I had used it in one of my jobs a long time ago. And then I started playing around with it because I was doing USB. I was one of the people that worked on USB, the specification, and I was doing barcode scanners. So I had to get my barcode scanner to talk to all sorts of different types of interfaces, serial ports, keyboards, and USB was a new thing. So I worked on that. And Linux didn't have USB support at the time. Windows did. So I started testing my device on different operating systems to make sure my firmware was right. Turned out I got it wrong. I was supposed to show up as a keyboard. My device showed up as a 102 key mouse under Linux. So it wasn't quite right. It turned out it was my fault. Funny thing is Windows worked just fine. I think Windows worked around the firmware bug. So I was like, okay, I can fix some things up in Linux. And I was following it. I wanted to do it for a while, and I submitted a few patches and it worked. And they took it and I got it accepted. And the USB stack was being rewritten from scratch at the time. This is the late 90s. And then my wife went away for a weekend with my daughter at the time. And she said, "Why don't you work on that driver for that device you always wanted to do?" I'm like, "Okay, sure, let me do that." So I looked at the Linux device driver book, and I wrote a driver for a device I had. It was a USB to serial port, and submitted it. And after a weekend, and I instantly got back, "Oh, this is wrong, this is wrong, this is wrong." And, "Oh, didn't you know about multiprocessors?" I was like, "Multiprocessors? What's that?" But it was great. It was like this feedback loop of I can be a better engineer by people telling me my code sucks. And that feedback loop was great. And so I fixed it up and submitted stuff and kept working on it on my own time. And over time, I realized that more people were using the stuff I gave away for free than the stuff I got paid for. Because my company I worked for was semi-successful, but it was okay. And I found a job at a different town in Portland, Oregon, doing Linux full time. And I didn't look back since. That was like 99. And so that's when I started working on Linux. And I worked for a number of different companies. OSDL, which was turned into the Linux Foundation, was in Portland, Oregon at the time. And I was involved with some of the people there. And I ended up being a core kernel developer and maintainer of different subsystems over time. I did the security layer, all the USB stuff, a lot of driver core work. And when the Linux Foundation was created out of the demise of OSDL, I was one of the kernel developers that kind of said, here's how it should work. And it was great. And I've always interacted with them and worked with them over the years. Eventually, the company I was working for at the time, Novell, was sold again. And I finally gave in and said, yeah, I'll come work for you, for Linux Foundation. And that was 12, 13 years ago. And I've been there ever since. But I've always been working on Linux. I've been working on Linux for different companies and whatnot. And that's the weird thing about Linux is because the person owns the maintainership or the core part of the kernel. It doesn't matter who you work for. So we joke when we see people next year, oh, who are you working for this year? It doesn't matter because that's the same thing. And companies learn that the hard way. I remember when I was working at IBM on Linux, somebody took over a subsystem of the kernel, was working on it, did a great job, became the maintainer of it. And then he was reassigned by IBM to do something else. And we're like, okay, that's great, but he still needs to have time to work on the maintainership. Like, what do you mean? We'll just give it to somebody else. We're like, no. That's his. He can leave the company. And that's true. And he did eventually left the company. But and I did too. But maintainership and ownership follows the people, not the process or not the company. And that's really interesting. So like USB, I've been working on USB since the 90s. Networking people have been working on networking core since the 90s. If you look at companies, if you want to go up in a company, you move around to different groups all the time. You learn different things. Windows has rewritten their USB stack, I don't know, 3 or 4 to 5 times now. There's nobody there who has done it for forever. So you lose that depth of knowledge. Well, Linux has this depth of knowledge and other open source projects as well, BSDs, that people just have been there for forever. They know this type of stuff because that's what they work on. I still know serial ports. Again, I've been working on serial ports for forever. So it's an interesting thing that we have this open source ends up having better resources or better depth of knowledge than closed source does. It's kind of funny.
How common this is that there are people that have like decade of worth of experience working on something. Like, is this a common thing?
In open source, yeah, very common. In closed source, no. And I mean, if you work for a big company, again, you move around between different groups all the time. It's not that common that you work on the same thing all the time.
So how do you have any idea how many Linux maintainers own their subsystems for like more than a decade? Like, what would be the percentage? Or
that's a good question. I don't know. We have like 700 maintainers. I mean, we have 4,000, 5,000 developers a year, so we have a lot of people. Okay. 700. I don't know. We have all the data there. It's all open. I bet at least over half, way over half. That being said, we still have new people coming in all the time. Every release we do is every 2.5, 3 months. We have 200 new developers that have never contributed. So we have a lot of new people all the time. And we have new people. We have subsystems that aren't maintained at all. You want a subsystem? You can take it. Or you come in and because you added a new subsystem because you wanted to support new types of hardware, then you're now the maintainer. So we constantly have new people coming in. I'm not saying we just have old, but we have the new and the old. It's really interesting, and it's something that other companies and operating systems don't have. I mean, Windows, I know a lot of the core Windows people are now working on Linux because they retired and they're like, oh, I want to work on something fun. Apple, OS X developers, I know a number of the core people that did that work aren't there anymore. There are still some there, but they're off doing other things. People who design some of the Apple hardware, they're not there anymore. It's just kind of funny that the depth in open source is you're much more experienced than you do in companies.
Yeah,
it's weird. It's not intuitive, right?
So since we're on this thread already, at what point in time let's say random contributor becomes a maintainer? Like, what needs to happen? Like, you can, in theory, just submit something, but it's not the point in time where you become a contributor, like a maintainer, right?
Sure. So, well, if you submit a new driver, you're the maintainer of that driver. you own it, right? I don't want to maintain it. Subsystems, if there's an existing subsystem that it already has a maintainer, depends. If it's an active one like USB, nobody wants to maintain that except me. There's other core developers. A lot of people don't want to be a maintainer because the maintainer is not new development. Mostly it's reviewing. David Miller, the networking maintainer, famously said once, we're an editor. We used to be a writer, but all we do now is critique other people's stuff. We say, do this, do that. And because we were a writer, we have a little side project, and I was submitting some side project patches today, but we're not doing new development. Maintainer is a different type of model. So I know there's a core contributor to the USB subsystem, and he doesn't want to be the maintainer. He just wants to review other people's patches and contribute at a time. It's like, great, I'll be the maintainer. I'll handle the patches. I'll handle the review. It's a different model, right? But again, it all just depends on what you want to do and what you're working on. Again, something new, you can take over the maintainership tomorrow. Something core, it's going to take you a while because it's all about trust. So maintainers and developers, it's about trust. You send me a patch. If I'm a maintainer, I now am responsible for it, right? So I have to trust that you got it right. So, or I have to fix it or whatnot. So a lot of stuff is I take code from people almost blindly because I trust them that they'll be there to fix it when they get it wrong. Because we always get it wrong, right? We're human. But they're going to be around and stick around to do that. So that's the core thing, is the trust. So it's really hard to change core pieces of the kernel because of that trust issue, right? You want to be able to know that somebody's going to be around, or I'm going to have to maintain it. Famously, again, the networking people years and years ago took some core features, and like a week later, after those core features were landed, the email address disappeared. So it took them like months to unwind the mess because now they were responsible for this mess. And that was a hard thing. So, and that's not a good thing overall to do. So trust is, it's a human interaction thing. So if you're sending me stuff that's only going to affect you, great, I'll take it. But if you send me stuff that's going to affect other people, then I have to watch it and maintain it and review it harder. And it's more interaction that way.
Okay. So if I want to become a Linux, or if I want to get involved as a person from outside, right?
Yeah.
What would I do?
Whatever you want to do. So we have some good first tasks. So there's a whole kernel subsystem called staging that just has really crummy code that just needs to be cleaned up, basic coding style issues and whatnot. And that's a great place to get involved. You can make a coding style fix, you can make a spelling fix, and you learn the tools, you learn the process, you learn how to submit the patches, you fix your email client because that's broken. It's just email. We just use email and Git and an editor, so it's very simple. And away you go. So that's the easy first tasks, right? How to do that. And if you go to kernelnewbies.org, it's a nice website, they have a link, first kernel patch. So here's how you do that and get involved. Your second and third, then it's harder. You have to know what you want to do, right? People have written up some good lists of here's how to get involved. Just build the latest kernel, our development kernel, and see what broke, or see what kernel warnings are there. Fix up a compiler warning. Get involved in a subsystem you want. I mean, we have hundreds of different subsystems in the kernel: USB, storage, networking, block, specific drivers. Pay attention to the problems people have. If you have the hardware, and you can see that people have problems, help them fix it. But it's get involved with what you're interested in, right? I can't tell you what to do because it's up to you to figure out what you want to do. If you really like timers, great, work on timers. If you want to do a new security model, great, do a new security model. So
Nice.
go from there.
Okay. Let's back up a little bit and talk about Linux as a whole, and maybe establish some sort of nomenclature, define some terms. I am very interested in like a technical overview of what is a kernel, what is the driver, how those two things interplay. When I think of Linux distribution, what is, let's say, the distribution part, what is the kernel part, and all these things, like how to think of it so that when I'm using Linux, I have a nice mental model for that. Can you give
Sure.
like a overview?
Sure. So operating system, that's the kernel. So a real definition of that is actually hard to find. The EU is trying to define that right now, and they're not doing a good job with some of their laws. But think of the operating system is there to manage the hardware resources. So Operating system, I joke, I make your mouse look like all other mice, right? It doesn't matter what type of mouse you plug in, they all will just work. Your keyboard will just work. So it makes Linux kernel provides a layer above the hardware to make it all hardware look agnostic. We don't know what storage you have. We don't know if that's really a network device, whether it's a storage device over a network connection, whatever you have. NVMe, SCSI, IDE, USB, whatever storage you have. So kernel's job is to manage the hardware and to manage the resources of memory, the resources of a processor, and then to allow you to run a program, a user space program, such that you think you have the whole machine. You don't realize that there's other programs out there, and so to silo all those little processes and keep them secure. So operating system's job, there's a technical point at where the processor will run in kernel space versus user space. It'll flip between the two. So the kernel sees all the memory at once. A process only sees its own memory. And it can't see all the other processes. So if you're writing a game, let's think of you write a game and talk to SDL, right? SDL is a great abstraction layer for the hardware below it or the operating system below it. But SDL provides a way to, give me a joystick. Doesn't care which joystick, just give me joystick number one. Well, the kernel manages all that down below. It manages all the joystick and makes the first one plugged in to be joystick number one. Same thing with mice. It makes all the mice look alike. So that's the job. And a driver in the kernel, so Linux, the model is a monolithic kernel. Our kernel is one big beast. It's all one address space. It's all one program running at once. So a driver is part of the kernel. It just is a driver, something that talks to hardware. So all different mice have different drivers, different keyboards sometimes have different drivers, but they all look like a keyboard, right? Different serial ports all look like a serial port. But versus a microkernel where you have things divided up. So a microkernel will have little tiny programs running in kernel space talking to each other, and that's slower. And that was the eternal debate between the different architecture people. In theory, microkernels should go as fast as monolithic kernels. In reality, they don't. People care about performance. In theory, microkernels are more secure than monolithic kernels. Maybe that's true, but there's not been any microkernels that's been successful to prove that. And then there's other problems. I mean, it turns out the hardware lies, right? I mean, we think hardware is perfect, but the job of a kernel is to fix all the hardware bugs. Remember Spectre and Meltdown? We were fixing CPU bugs where processes were leaking through the CPU. We have tables and tables in the kernel drivers to fix up your mice because, the mouse is reporting things upside down from the other mouse. Your sound card is working with a little different quirk. This USB device has a little not standard quirk. So the kernel's job is to fix up all the little hardware bugs. So that's the kernel, the lowest tiny level. And that's what Linux is. No graphics, no anything. It provides graphics access to hardware, but no graphics on its own. And a Linux distribution is a whole bunch of user space programs on top that bundle things together into a usable system. So Linux famously doesn't need a Linux distribution. Look at Android. Android took the Linux kernel and rewrote everything else. They did the whole thing they didn't want to deal with. They didn't want to do anything else. So much so that you can overlay a whole Linux distribution on top and it'll run at the same time, which is pretty cool from a technical point of view. So Linux is at the bottom, and then all the user space programs at the top. So Linux distribution, let's say Debian, has the kernel, Linux, and then a whole bunch of user space programs. And those user space programs are common among the open source operating systems, like the BSDs share the same shell, the same editor, the same X window system, which is the graphics. Wayland is now the graphics system on Linux, but that's a different graphics system. And then you can write your application for Wayland to work on a graphics subsystem to handle the windows and things like that. And SDL has a Wayland back compositor, has an X compositor, has a frame buffer compositor. If you don't have any graphics card, just a raw frame buffer. So that's the different levels up there. So the kernel, one big program running at once, individual user space programs on top of that are isolated in a secure way that they can't talk to each other. And they can talk to the kernel through well-defined interfaces. We have that interface between the user space and kernel. It's well-defined. We never break that. If we break it, that's our fault and we'll fix it, because we always want you to be able to upgrade the kernel without feeling like you're going to break something. And that's our goal.
Can you repeat that? Again?
So the kernel has ways to talk to the user space. User space has ways to talk to the kernel, like read. You want to open a file, read from a file, write to a file. Those are common system calls, they're called. That interface is an API. That's an API that we guarantee will not break. So that if you update the newest version of the kernel, your user space programs will just work. I have user space programs from the 90s that work just fine. Now, Linux keeps adding more and more new functionality. The new stuff will work as well, but the old stuff will continue to work also. And that's our guarantee to everybody. And Windows has the same guarantee. They guarantee that their old stuff still works. So it's not a new idea, but it's just common.
Okay. So for example, when I open a file, there is an API call, and sometimes it's called like system call, and it's like there's a bit of difficulty for me to distinguish where in the stack am I with the names, because like you can have a library, right? You can have an API call. There's a term system call. There's also like at some point kernel takes over from the user space. So it's like, what would be the stages of like opening a file from the perspective of the program running in the user land? Like,
so user space can call open, right? And then in C, let's talk about C. C has a standard library called glibc or musl. There's others. And that open call is usually a wrapper in the library, libc, that does a few little housekeeping things and then calls the kernel's open call. And it's called a syscall down there. So there's a raw syscall layer. If you want to, you don't need to write libc. You can write, I'm going to call syscall number whatever, and it's open. And all system calls have a number. That's the way they communicate between the two. Libc will wrap that number in a fancy name called open. And it returns a handle, and now you have a file handle. And now you pass that to read, and read will go down to the system call read. Read will fill in the buffer with anything that's there and report back up. So there is a system call called read, called open, whatnot. If you type man, you can look at the man pages. You can see where the system calls are. But most of them are mirrored in the library, libc, to make it easier for user space programs. Because the error handling works better in user space, it handles some common errors. But then look at other languages like Go or Rust. They don't have a libc, it's built in. So their libc is built in, so you call read, and it calls directly down into the read for this architecture and doesn't have a libc. Go is the same way. They built it right into their standard library. It's built in right there. It's not a standalone library.
Okay. So now when you're working on a kernel, you are changing the code that will run in the kernel mode. And by definition, you're like constrained much more than
very constrained. Yes.
Us in user land, user space. So what are the differences? What are the tools that you use to develop the code? Like, how do you work?
Oh, editor. I mean, editor, compiler. nothing fancy. Vim is my editor, compiler, and make. Git. We wrote Git. I mean, Git was written for Linux development. But you build it and then running it. Running is the hard time. I can reboot my machine and run it. Works great. Or I can boot into a virtual machine, because now we can do virtual machines. If I'm doing code that crashes at boot time, I'm booting in a virtual machine because I can't figure out what's going on. Most of the time, it's just I reboot in my real machine and away I go. And it's hard. So there are some debuggers, but most of us don't ever use debuggers. So the equivalent of print to the log to figure out where you are, print to figure out what you're going on. Very constrained resources in that we have no stack, almost no stack at all. So we don't put anything big on the stack.
Why?
Stacks are very small. So I think it's 4K, maybe 2K, depends. Overall, and you don't know how deep your call chain is going to be. So you don't put anything big on the stack. You dynamically allocate what you need to do, and then you can free it up later. But you don't put big things on the stack. It's just because we need to have the kernel's resources are very limited, because we want to give all the resources to user space. Let them do whatever they want with. Because all the memory that the kernel uses is not swappable. It's not able to be used by anybody else. So we want to be able to use the least amount of memory as possible. We can dynamically allocate memory, but again, if we dynamically allocate memory, then user space can't use that memory. But if we declare stuff on the stack, we don't want to mess with that at all. So very constrained resources. And C, we write our code in C and Rust. So there's some Rust code now. And there's some little assembly language, but very few people use the assembly language stuff. Like a boot time and a few odd things. And that's it. But it's just very resource constrained, raw C code. It's very simple C code. It's not complex stuff. It's very well documented, very well written. We write code for people first, compilers second, because we know we're going to have to maintain this stuff for forever. Famously, you've made it when you look at some code, you're like, who wrote this? This is horrible, horrible stuff. And you look back in the log and you realize that was you. So that's when you've been around a little too long. But no, that happens all the time. So then you go fix up your code. Away you go.
You said a nice quote, like we write the code for people first, compiler later. This is the quote.
Compiler second, yeah. So because we're the people that have to write it, right? And I always wonder, like, people start writing code first before they read code. Read the code. I mean, that's how we do debugging. We read the code. We try and figure out what's going on, because we want to make things as readable and understandable as possible. Because I want you to fix my bugs. I'll fix your bugs. So the review process is very, very important. We want to make things obviously clear, and I want to make it, you want to send me a change that's obviously right. It's like, oh, of course I'll take that. That's completely going to be right. I don't want to see some complex, crazy stuff, because then I won't know if it's right. And do we trust that? And how are we going to maintain that, right? You want to make stuff simple. The kernel is very, very simple C code. It's not complex stuff.
So it's simple code, but it's a lot of it. That's the complexity.
It's not, so, I mean, we're 40 million lines of code overall, but that's all hardware, all devices, all architectures. You only run a very, very tiny bit of that. So my laptop runs maybe 2 million, 2.5 million lines of code, depending on what hardware I'm running. A server runs 1.5, maybe 1 million. Servers are really, really simple. That's the least amount of code. Your phone is the most complex beast out there. Those are running like 3.5, 4 million lines of code. Those SoCs on those phones are just complex nightmare. Those are running a lot of code. But again, 4 million lines of code out of 40 million lines of code. So you're always running a small. Everybody runs core bits of the kernel, but then it's depending on what drivers, depending on what hardware you've picked, depending on what options you want, is actually built in there. So it looks like a giant tarball. Again, you're only running a small subset.
Is there a person that knows, like, roughly 100% of this code? Like, I know, like, line by line it's impossible, but like I talked to the person Marcin Undak, who works in AAA industry, and he told me, like, imagine, like, you hire a couple of hundred engineers to work on a AAA game engine. Like, people will produce a lot of code. Like, you are not able to keep up. Okay, like, it's not possible to understand everything. But Linux is around, and this code doesn't change that much, I presume. So is there like a person, or is there many people like that have like a good mental model of whole Linux kernel?
No.
Okay.
I mean, it's too big, right? So I can understand the general, right? I know parts of the kernel very, very well. I know other parts not well at all, but I know how to find that. I mean, look at graphic cards. Graphic cards are beasts. Those are almost a whole kernel in themselves, because they're controlling all these crazy GPUs and schedulers and resources, and that's a nightmare. If you look at the size of code, those are almost as big as the core kernel for a graphics driver. But there's memory management subsystems, there's CPU, there's driver core, there's this virtual file system layer, which is very, very complex and crazy. Linus knows that really well, along with another core, a couple of people. I know the driver core really well. The networking stack is different, but we all specialize in different pieces of it, right? We have 700 maintainers, maybe 100 core maintainers, and we know where to do that. The good thing is we all know where to find the other people, right? So, like, the security, I'm part of the Linux kernel security team. When a security bug comes in, if the few of us that see it triage it, like, yeah, there's a bug, then we go grab the people responsible and drag them in, right? We're not going to fix it because we don't know that area of the code. So it's just, we know how to find it. Every line of code, it can be tracked down to a maintainer and somebody who reviewed it, right? So you can look at the whole kernel tree and say, okay, this person wrote it and this person reviewed it. So you can figure out who did what. You can look through the Git log of the history and the history before Git, figure out where things came to and why they were made and why they were decided. So nobody knows everything. Of course, it's too big and complex, but we can all figure it out, right? Some nasty, tricky things are, hopefully, we all know those, like the virtual file system layer. There's some things, but we have backups for maintainers. We have maintainer pairs. We have lots of multiple developers on different subsystems. So the load is spread out pretty well. but nobody knows it all. Just that would be impossible. And you wouldn't want somebody to know. I mean, that's you don't want that. You want people who know the ideas and are specialized in different things, right? So that works out.
Yeah.
Just like a game engine, same idea, right? It's the same thing.
I wonder, like, if you make an error and you will find out after you reboot the system, it is quite punishing development loop, like a cycle. It's like, I'm writing this code, I need to restart my machine, and if I made a mistake, I will learn in some time. How, like, does it help you run like flawless code with this kind of training?
Yeah, it does. I mean, rebooting's fast now. It used to be slower.
Okay.
So we can boot fast now. Yeah, it is. It's punishing. It is punishing. And like I write some user space code. I'm like, oh, this is so easy. I can just I can write a unit test. Oh, this is awesome. So user space code is very, very simple that way. You have debuggers, you have flame graphs, you have all this stuff. We do have a lot of debugging tools. We do have a lot of static analysis tools. We got a lot of runtime analysis tools to check things. We have locking dependency graphs, lock checks at runtime to track down nasty things. So we have a lot of debugging tools at our disposal. But yeah, it does take a long time. And I mean, we don't have debuggers to step through code. We read the code. We try and figure out what's going on and try and reason about it. The nastiest issues are when there's timing issues, right? This process is doing this and this is coming in at the same time. And oops, we forgot to grab a lock or something, or we're writing over something, or race conditions. Famously, I had a bug that like it would only work if I was doing something and yanked a USB camera out at the same time. It's like, how do I debug that? So just the reboot time took forever. And sometimes it's like, oh, it works for me, but why doesn't it work for you? What's different about your hardware from my hardware? And oh, the hardware's a little bit different. Oh, the timing's a little different. Oh, you built with a different compiler. Oh, is that a compiler bug? Is that not a compiler? Oh, we go through all sorts of things. Yeah, it's not simple stuff. User space is much, much easier.
Okay. And you only use print debugging for that.
Print debugging is great. And especially with a virtual machine now, you can spin up a virtual machine and have all the debugging going out to your real machine, and it's simple to do that. Now, if you're dealing with hardware, yeah, it's a little harder. You have to do it on the real hardware. But again, you can print messages and see things out. Crash, you have kernel crash dumps. Read the kernel crash dump, figure out what went wrong, go from there. Okay, why did that crash? You can see the traceback, you can see the symbols. Why is that crashing there? What does that looks odd. Why is that variable? So yeah, we think about it and reason. Again, write the code for people first. So we want to read this stuff.
Okay.
But it isn't that hard. It's difficult. It's just a skill. I mean, it's nothing complex.
You mentioned something quickly, this difference in the approach between the monolithic kernel and the microkernel. Can you spend a little bit more time to say, like, what would be the idea behind the microkernel and the monolithic kernel? Linux is obviously a monolithic kernel. I think Windows is microkernel.
No,
Okay.
Linux, Microsoft Windows is a monolithic kernel.
Okay. So what would be the microkernel architecture? Why would it be better in theory? Have it been really tested? Like, how has it been tested? Like, how does this look like? What's the differences?
So Minix was a microkernel. I learned on Minix. Linus learned on Minix at the same time. We're the same age. Fuchsia is a microkernel. There's a bunch of other microkernels out there. Microkernel is the goal is to divide up everything into tiny processes. So your core kernel is not running in the same address space as a driver, right? So if your driver crashes, it can't affect the core kernel. That's the goal. So you would only be able to communicate. Remember how I said the kernel on Linux protects processes from each other, so they can't access it. So a goal of a microkernel is to protect parts of the kernel from itself. So you only talk through well-defined interfaces, be it a message passing idea. Herd's the GNU. That's a microkernel. I think it's a microkernel. I haven't looked at it in a long time. You pass messages. So a driver would have to say, I want to get access to IRQ. So here's a message there. And then when the core kernel gets a interrupt, it'll say, okay, hey driver, here's a message saying you got an interrupt. Go do something now. And then if the driver crashes, it can't go and crash anything else. The monolithic kernel is all our code is in one big address space. Any driver can scribble over the memory of anybody else. right?
Yeah.
I can grab the resources, I can run a wild pointer and go crazy everywhere else. So, but when the kernel gets an interrupt, it just does a function call straight into my driver. Away it goes. So it's faster. It's instantly faster. We have some things that are even, we have jump tables for drivers because you can load a driver at runtime. And so I'd be, okay, which driver function do I call there? And like a virtual table, C++. We have a lot of object-oriented code in the kernel. We do C and inheritance. We do inheritance in C. It's crazy. Yeah. Sometimes I wish we had C++, but no, I really don't like C++. So we have virtual tables, and when you load a file system or you load a driver, that way we know which driver to call for the storage device. But sometimes for speed, we'll rewrite those tables to be just a direct function call, like network stack. It's some fun stuff you could do. So speed-wise, a monolithic kernel wins. Security-wise, a monolithic kernel does not win because you have to trust all of this code, right? It turns out speed matters. Right? Speed is the equivalent of power. So Fuchsia, famously, is a nice monolithic or microkernel architecture. Some operations take 3 times longer to toggle a GPIO pin up and down, up and down, up and down. It takes 3 times longer because you have to pass the message. 3 times longer means 3 times more battery.
Yeah.
So power matters, right? Power and resources matter, and time and speed. So in theory, it's a wonderful idea. In reality, fix your code, right? Update your code, make sure your driver works well, and away you go. Yes, if things can crash, and do that. We now have things in the kernel to help mitigate problems, right? We do a lot of static analysis. We have a lot of runtime things that we catch problems at runtime. If we do go outside of bounds, we have a lot of bounds checking. We're adding more and more bounds checking to the compilers and things like that. Like Rust has showed us some really good things we can do. So we aren't writing raw C code anymore. It's much safer C code, but you can still scribble over things if you want, but it's a bug and we'll fix it and away we go. Microkernels are a wonderful thing to theorize and to talk about from an academic point of view. Me and Linus and others argue reality kind of matters.
Okay.
But there's some good microkernels. SE4 is a cool microkernel that's been used in a lot of things. There's some other stuff. Microkernel QNX, I think, is a microkernel in certain ways. They're out there and they're good for some things, but some things it's not.
Okay. I view it now as more of a academic kind of experiment than the real life approach.
Yeah, it is. But academics are great. I mean, I work with a lot of university professors and taking those ideas into things that they can maybe make our stuff better. And it's good to learn those ideas and figure out what we can do better. Figure out where they failed and where we failed and where we can come up with better ideas. So,
okay. When you famously have seen every security bug, and that was
yes,
at least
yeah.
So what are the standard problems that happen in Linux code? Like, what would be, if you were to extract like the most common issues, what really happens?
The most common issue. So yeah, I'm now responsible for issuing all the CVEs. Been on the security team since the beginning. Most common, like real security issues, are untrusted user space data. So data from a user space that we don't validate properly, right? Okay. So you give me some data and I'm parsing it incorrectly, right? Or you give me some data and I didn't check how big the data was, right? Untrusted user space data. That's the biggest problem over the years. That's the most severe issue, right? Now we have tools to track user space data to make sure that we validate it before we access it. We do things a little better than Windows does in that we copy data. We don't access it directly in place. We always copy it from user space first, so then we can validate it, and we don't have to worry about you changing it after we validated it. Windows has a nasty problem with that because you still control your data, right? You don't want to be able to modify it. So that's the biggest one, user space data. But the majority of just bugs that we have are stupid ones, off by one errors in array counting, things that the compiler can catch now. Forgetting to check your error values, right? Oh, did the function really return? It didn't return a valid pointer, but I treated it as a valid pointer, but it really was null. Oops, I crashed. So a lot of those are just dumb and we just crash and you reboot and away you go. Those are the majority of the stuff. So stupid. But untrusted user space data is the nasty one. And also untrusted network data coming in from the network, right? And then are coming in from a Bluetooth device. Right now, Linux's model is that we trust the hardware because we always thought we had trustworthy hardware. It's looking like we can't trust hardware anymore. We have some good fuzzers out there that'll make it look like a fake USB device, and they'll fuzz the part of the USB stack. And we've now fuzzed like the top level of the USB stack. Don't know how far down deep we want to go
What
to
does
fuzz.
What does it mean?
Fuzzing is cool. So you can make a tool that will just start giving you random data, right?
Okay.
I'll make a fake USB device, but make one of the fields a little bit wrong in the structures that the USB structure is supposed to look like. And then what does the driver do? Does it trust it or not? Famously, we had some really nasty bugs where you plug in a fake device and then we could overflow some buffers and then crash the kernel. And we fixed them and away we go. And there was actually a bad one that happened last year where you can plug in a fake USB camera to your phone and unlock the phone and get full access to it. Yeah,
Nice.
That was a good one. That was a good one. But so the original model of operating systems was we trusted the hardware. So we've now maybe we don't need to trust all the hardware. So validating the data from the hardware, you don't want to do it on every single bit because then again, that slows things down. So where do you draw that line? And it gets tricky. But data validation, it's the security 101.
How much of these bugs and issues could be caught if you were to use Rust as if you were to magically wave your hand and turn everything from C to Rust?
I think I said half. Somebody says that's too low.
Okay.
Seriously, Rust solves so many of our problems just for the simplest things that Rust was designed for us, right? Again, Rust core developers were like, we want to write a system stuff that we can write an operating system. And some of the core Rust developers are ex-Linux kernel developers, so they know this stuff. Error handling, you have to always do the error handling properly or the compiler will complain about it. Borrow checking, you pass around pointers, you have to know who owns that pointer at all times. In C, we pass around pointers all the time and oops, I forgot the reference to it, or I overflowed the reference, or I didn't free the reference. That happens all the time. Rust won't let us do that. And the error handling and the simple bounds checking, there's half the bugs that we get all the time. Now, those are simple bugs. They're not severe bugs. They're just bugs that, oops, the box rebooted and away you go. Or they only happen under very extreme situations, but you could trigger them somehow. I think a lot. That's why I'm pushing for Rust. I mean, that's why a lot of us are pushing for Rust for a lot of stuff. It's a good idea. It's going to solve our problems instantly, and that's good. So new code can be written in Rust. It's cool.
Yeah. Can we zoom in on this? How do you envision the introduction of more Rust code to the Linux kernel? And what's the state now and how it will change in the future?
So we're not going to delete 40 million lines of code and rewrite it into Rust. The problem, so everybody's like, oh, we'll just write a driver in Rust, right? Let's just write a driver. So the problem with drivers is a driver consumes from everything in the kernel. You want the basic data structures. You want linked lists. You want core functionality. You want these calls. Linux drivers are famously 1/3 smaller than other operating system drivers because they rely on a lot of shared code that all drivers do. So it's easy to write a driver in Linux. So Rust, in order to write a driver in Rust, you have to write a binding between the C code and the Rust code. And these bindings are tricky, right? And they're hard to write. It'd be simpler to write core Rust code in the kernel, and then you wouldn't have to worry about it. In fact, some of the first Rust code that we have is some core Rust code. When the kernel crashes, the graphics system will display a QR code with the kernel crash dump. That QR code generator code is written in Rust. It was a simple call into it, generate a QR code, come out, go. Famously, here's an example. You can write bad code in Rust. The Rust code was given a buffer and a size of the buffer. The Rust code forgot to ever check the size of the buffer. Again, valid. And the Rust, you can write valid Rust code. It was like scribbling over memory just fine. But yeah, we have to. You still have to write good code no matter what. You can write bugs in Rust just as easy as you can write them in C. The fun thing about Rust is when Rust crashes or it causes a problem, it'll just reboot. they'll panic. You won't be able to exploit the problem. So if you write out of a range or you run out of a resource, you're just going to reboot, which is safer in a way. You'll still get a CVE, but it won't be as severe. So these bindings are tricky and they're hard to write and they're nasty. And it's really complex Rust code. So you need to write bindings for a lot of different parts of the kernel in order to write a driver. So right now, people have been going through and writing bindings for a lot of different parts of the kernel. And now we have enough bindings that you can write simple drivers. You can write some a platform driver. You can write a MISC device driver, which are just simple type drivers. You can write a PHY driver, which is the thing that controls the clock on your network card. People wrote that. There's out of tree code. People are doing a lot of this work for two things. The binder driver for Android, which is the way it does inter-process communication, is written in Rust, and the developer there, she's written a lot of bindings to try and get that working. It'll get there eventually. And the new NVIDIA driver are being written by NVIDIA and Red Hat for GPUs is being written in Rust. So a lot of those bindings are coming from those developers. So we have a lot of core Rust code that's not being used, and eventually we'll get some real users. So you're starting to see some stuff coming in. So new code coming in. Don't want to delete don't rewrite old code. New stuff coming in. It's going to take a while. That layer, the kernel has its idea of how it handles objects and models, and like the driver core, which I helped write, it has its idea of how it's going to handle C objects. And then Rust has its idea of how it's going to handle objects. That intersection is really, really tricky. I know Rust okay. Writing bindings is hard. It's just some complex code. So we have some really, really good Rust developers right now. And so let's take advantage of these people. They're amazing developers. They're writing some really cool stuff. Like one of my subsystems, I have a debugging file system that I manage. They're trying to write a binding for that. It's taking us, we're still not arguing, we're still discussing it for weeks on how to write a proper Rust binding to interact with the C code in a way that's going to work out and be easy and provably correct, right? Because it's really easy to get these C APIs wrong. API design is tough, so it's hard to get these APIs right and work through them. It's going slowly. It's happening. And if you want to come and drop a new driver on us that's in Rust and all the bindings are there, I'll take it tomorrow. It's not a problem. But it needs new stuff coming in. I don't see us rewriting old stuff. It just doesn't make sense, because then you'd have to, why would you rewrite old stuff?
There is a lot of like smaller projects being rewritten in Rust from scratch, kind of for the sake of it. Like, like here's a small library or a small like database, like, but it's from scratch written in Rust. But Rust for a Linux kernel, 40 million line of code, not necessarily.
No. Well, so the tools that we use to manage the CVEs for the kernel, I wrote in C and Bash, a whole bunch of Bash script. We rewrote those in Rust. So we wrote them from scratch in Rust. Now they work faster than Bash. A friend of mine many, many years ago, a programmer said to me, "Oh, you should learn more Rust. It's actually fun again to write code." I was like, it's fine. I like C. And I should have taken his advice, because actually writing code in Rust is fun. It's a fun language to use. And it makes it when you realize, the compiler's keeping me from doing something, maybe that's a good idea. You shouldn't be doing that. Think about that for a second. So Rust's compiler will catch a lot of the common errors that you make much easier. And then when I switch back to C code, it's like, wait, I got to think about who owns that pointer now, and where's the life cycle of that, and I got to check my error values, and it didn't tell me I forgot to check the error values. And Rust is a fun language. There's other fun languages. Zig is a fun language. Hair, Go are fun languages. But why the Rust is also because the people are showing up to do the work. So I'm not going to turn people who's willing to do the work away. Right? They're going to do the work, great.
So do you see the future of Linux having more than these two languages? Like if there were people like now Zig people joining the Linux project, pushing for Zig in kernel,
they'd have to convince us why. The Rust developers came to us and convinced us why, and they showed us how it would work, and they proved that it could work, right? If the Zig developers want to come and do that too, wonderful. I think I heard somewhere the Zig developers don't care, which is fine. That's fine. These are people that, we're not going to turn away people to do real work. So we'll try. It's an experiment. If it stops and goes away, We're still have our functional kernel, and it all works just great. I want to see it succeed because, again, I think it can actually solve a lot of the bugs that we have and keep doing over time. It'll let us evolve in a way that's more secure, and that's good. It's fun. There's people still working on the GCC and the C Clang in order to fix our C code, because that's very, very important too. We have people working full time on hardening the kernel and hardening the C code, and that's very important, and that's never going to go away. But I think we need both. Both is a good thing, right?
For the C code, do you have, for example, like a style guide? Like you can write C code in so many ways that,
Yes.
and you have a lot of people that need to somewhat agree on the style of C code. So do you have like a shared common version of the style and the techniques and mechanics, or is it like you own the subsystem, you do whatever you want, but as long as you...
No. We have a style guide. We've had a style guide since the beginning. You will see some very, very old code in the kernel that was before the style was enforced. That's still there. SCSI layer famously has a lot of really old stuff. And just don't touch it. Nobody's touching that code, so it's fine. old drivers that nobody uses anymore, fine. But we have a shared style guide. And the style is there for a reason. It's not necessarily that it's the correct style. It's just that it's a style that we all agree on, because our brains run on patterns, right? If you show me code that's written in a different style, my brain is like freaks out, and I have to spend some time looking at it and figure out what it's doing. If you show me in the same common style that I'm used to, that metadata goes away, and I can see the logic, and I can see where you get things wrong and see stuff like that. So style is there for our brains, not necessarily that it's the right or wrong one. So Linus laid down some rules in the very beginning. We've kind of formalized them and made maybe some pedantic, too pedantic in places. But there's some basic, like some subsystems comment things in a little different way than other subsystems do. Fine. That's not a big deal when you want to argue semantics. But no, tabs, 8 columns, real tabs, braces go here and here, things like that. Functions look like this. Comments for functions look like that. That's important because you want other people to review your code, right? We want more people to do that. So we want to share a common style. All big code bases should have a common style just for that reason, just for your brain. It's a people thing again. Not the compiler doesn't care. It can all be one line, right? Yeah. This is a people thing. So yeah, style is good. And that makes it, you feel comfortable. You can jump into other subsystems and not worry about it too much. I was just editing and changing an API that I was hitting like 40 different subsystems. Like, great. Nothing looked different everywhere else. Just had to go fix things up.
What about the actual data structures and some sort of mechanics? Like, do you have an enforcement on like, oh, we should use this or prefer this type of solving some problems with these data structures, or you should rely on these, not on the others? Like, is this?
Yes. Oh, definitely. We have, we have lists, pointers, we got red bleat, black trees, we got double A linked lists, we have reference counting objects. So don't reference count your own stuff with an atomic. Use our reference counted objects because they'll handle proper flooding and underflow and overflow. Use the objects and the structures that we have in the kernel for that. That's a good thing. And that's really also important for reviewers. If I see you rolling your own reference count, if I see an atomic variable that you're trying to do, now I have to go and make sure, did they get it all right? But if you use the structures and the APIs that we have in the kernel for reference counting, great. I know you got it right because I know that's just going to work. So it's good. You should use these things, and they should have no speed overhead, or it should just work. Sometimes there is a little bit overhead, and maybe you can get away with not using them, but you better justify it. You better have some really good justification and put it in comments saying, this is why I'm doing this because of X, Y, and Z. For most of the times, in the kernel, speed doesn't matter that much because hardware's slow, memory's slow, disks are slow. But for some parts, it does matter. Right? There's definitely some paths that are very hot and very fast. So some of those might look a little strange. And so those are written for that reason. But usually the comments, there's more comments than there are code, usually in that section. But we have, lots and lots of common data structures. And when we see people doing the same thing all the time, we make a common data structure and we convert everybody to use it and fix bugs. Like when we fix the we finally, okay, we're going to do a common reference count structure. Let's use it. And let's sweep the tree and convert everybody. We fixed real bugs. We found bugs that nobody had ever noticed. Oh, yeah. So that's good to use these kind of things all the time. So yeah, we have lots of stuff like that, lots of common libraries. If I see you doing something that looks like it should be in a library, It's usually you forgot and it was there. We just you didn't notice it, or then maybe we need to go at it. We'll at it.
Yeah. Nice, nice. Uh, so what are the difficulties then? What are the most difficult part of Linux development?
Fixing hardware bugs. So,
Oh, really? Like
yeah, I mean,
in such a big project and so many people involved changing various other parts, it's still the hardware that is most like
okay,
difficult.
well, that's all right. So I deal a lot with drivers, and so no, I mean that's the trick, right? Because there's an infinite ways that hardware engineers can get things wrong, right? And blame us for it. No, that being said, people are always the problem, right? It's development process, it's arguments between people, it's things like that. People are always the hardest thing to manage. Whatnot, we're big, wet, squishy bags of water. Hardware is at least semi-logical. That's the biggest thing. So once a year, the core kernel people get together and we talk about our process. Is things going well? Do things need to be changed? Whatnot? And we've been doing that for the past 20 years. And that's the key. As in, we adapt our model, we change things here and there as things are needed, and we listen. And the cool thing about Linus and me and hopefully everybody else in the kernel development is you can convince us we're wrong and we'll change our mind. If you say, hey, no, we should be doing things this way instead, it's like, yeah, maybe we should. Let's try that. Like Rust, let's try that. Okay. So we change our model over time. But a lot of the stuff I deal with is just, okay, this breaks on that hardware. Okay, let's fix that piece of thing up. Or little nuances here or there, or other things broke. But it's just like any other software project. It's unique in the software project is that our rate of change is insanely fast. We're still going at 9 to 10 changes an hour, 24 hours a day, 7 days a week. We've been doing that for 15 years. And we have 5,000 developers. 500 and 600 companies.
What?
Yeah, it's huge, right? But our rate of change is huge. And the rate of change is proportional across the whole tree, pretty much. So the core kernels, say 5%, 5% of the changes is in the core kernel. We're changing things because we have to change things. Most software projects, they have a big ramp up to do a lot of work, and then they taper off. Kubernetes, a lot of work, now it's tapering off because they solved the problem. Kernel, famously, one of my managers at IBM for years, he would come to me and say, hey, is Linux done yet? And I was like, no. And I finally realized I should say, hey, it will be done when you stop making new hardware. So the only reason we're changing things is because people want it to do something, right? They're adding new hardware types, or using it in a different way. Everybody contributes to Linux in a selfish way. They want to solve their problem. Linux worked for me 20 years ago, worked for Linus 30 years ago. So it solves our problems, but we wanted it to solve your problem. You can contribute a little bit, solves your problem. Turns out everybody has the same problems, right? So it works for everybody. You solve a problem for one class of things, it works for everybody else. Famously, power management. Embedded people said, we really care about power. We want to run batteries years and years ago. And Linus, and people said, no, go back and do it so it works for everybody. Make it generic. Work for everybody. They're like, nobody else cares about power. Like, make it generic. Turns out data centers now save billions of dollars in money because it's more power efficient, right? Everybody cares about these things. Everybody's special and unique, just like everybody else, right?
Yeah, exactly.
So the same common problems with everybody. So Linux changes a lot based on the world changing. And if the world stops changing, then we'll stop changing. If we ever stop changing, it's either we're a dying project or we've solved the problem. And I don't think we'll solve the problem. New hardware keeps coming, new use cases keep showing up all the time. People keep trying to do weird and crazy things with Linux and send us their little patches, and away they go. Because they can contribute. It's like you get an operating system kernel for free, and you can, if you just change your little bits to make it work for you, submit it back and solved your problem. Away you go.
So for what are the primary movers now in this world? Like what at some point in the past it was embedded, for example, like there was like a big project and big chunk of effort. What is now like a thing on the roadmap that is the closest, that sucks up a lot of the effort?
Well, we don't have a roadmap. We have no plans. So famously, it's not intelligent design, it's evolution. We react to what people send us. right? So if
Okay.
you have a problem and your problem, and you send us the code and the changes. We don't work on the idea of you submit a proposal for something you want to do, right? Of, oh, wouldn't it be great if you guys did that? We want to see working code first, because working code might not be correct code, but it proves that you solved the problem, at least it's possible, right? And we can iterate from there and go from there. So the big problem areas are new hardware types, new hardware models, new threat models for different types of security stuff people like doing. eBPF is a layer that you can do tracing in the kernel, and that's taking over because it turns out that's very useful for everything. Now you can write a scheduler in eBPF, as well as you can write a HID driver for your mouse in eBPF. As a network packet sniffer in eBPF. It's just data flows, right? So eBPF's taking over the world because it turns out that's a good model. It's not a microkernel, but it's a way to isolate running code in a sandbox within the kernel in a way, which is cool.
Okay.
That's a fun thing, but people are working on that because they want to solve their problems. People want to solve their problems. Embedded was a huge problem in the beginning, but I mean, Android is what, 5-6 billion devices running Linux? Everything else is a rounding error. I make the data server people mad when I tell them that. You're just a rounding error. Don't worry about it. Android matters, right? Android's the biggest user of Linux. And after that, it's other embedded stuff. I mean, Linux is everywhere. It's in my dishwasher. It's in my washing machine, my power meter, cars. I mean, the windmills in Europe, all the turbines, steam turbines in the US. It's cow milking machines, satellites. It's everywhere. Air traffic control in Europe. Yeah. All the financial districts.
Yeah, that's a different view that you usually have, like, because a lot of especially developers think of like, oh, servers, right? Like servers
Yeah.
is the primary thing. Like we care about servers and the software and web servers especially. And
We do care about that. And those people are actually some of the companies that pay developers to work. But I mean, Facebook has a lot of number core developers in the kernel, and they can get those cat pictures going really fast. So look at that. But Red Hat's also doing work for NVIDIA to get the GPU stuff working really cool. And you have other stuff. Android does their specific stuff. Qualcomm brings their chipsets up and gets their Intel does their stuff. AMD. I mean, every hardware company wants Linux to work for their hardware because they want to sell chips, right? So that's the primary people who work on Linux is the hardware companies, and then the developers who work for the individual companies as well, because they want to get their hardware device to work. It's great.
how is it then, especially in those contacts? So I can imagine that you have a lot of people and a lot of companies very invested in making Linux work for them. And how do you organize this? So for example, Intel has their own CPUs and AMD has their own CPUs, and NVIDIA comes with GPUs, and then AMD comes with JGPUs, and like it's like we need this, we need that, we need this, we need that. Like how does this flow into what is happening in Linux? How does it work
Very
out?
hard. So GPUs. Let's talk about GPUs. So Excel graphics is a common interface. You want to give user space a common interface to the hardware so that it'll work on any type of hardware, right? GPUs are famously very different from each other. So the graphic driver authors have to come up with a middle layer that works common for everybody. Making that middle API, that DRM, that graphics layer with Mesa, interacting with that is a tough job. And those developers do a great job at that. That's a tough thing. So if you come in now with a new graphics card, okay, here's the API I need to write my graphics driver for because it'll just plug in and it'll work for anything else. Same thing with mouse. You're going to come in with a new type of mouse. Great, you know what the API is and whatnot. But when you have new features coming in, then you need to start working together, right? And this is actually the reason the Linux Foundation is there. So Linux Foundation is a trade organization, and legally companies who compete are not allowed to talk to each other. It's just monopoly laws, right? But they can talk in public in a trade organization. So you go to a conference, Intel and AMD and IBM and all these companies could sit down and say, hey, specifically, there's some confidential compute APIs we want to come up with and a common factor so that all our hardware will work. Well, let's sit down in public and create an API. And that's what Linux Foundation does. It helps facilitate that. We run lots and lots of conferences. They have meetings for different subsystems, and they do that. So not very few people work for the Linux Foundation. 3 of us, 3 developers. I always joke we have more accountants than developers.
What?
Yeah, three. Me, Linus, and Shua are the only kernel developers working for the Linux Foundation.
Okay.
Yeah, everybody else works for companies, right? So it's just the way. We're the only 3 that like can work on whatever we want to that way. Other people working for other companies can work on whatever they want to, but that's their decision. So yeah, Linux Foundation is just a facilitator to trade organization for that type of things. So Intel, like confidential computing, they're working on a common standard that'll do a common API that you can control confidential computing stuff. Famously, though, IBM already did it on their S390s, which is their big mainframes that run Linux. So I didn't threaten them, but I said, hey, if you guys don't agree, we'll just take the S390 model because that's already done. So S390s, the IBM mainframe stuff that runs Linux is amazing. You want to see where hardware is going in the next 10 years? Look at what they're doing today. They did everything first, like hot plug CPUs, multiple memories, yanking out things, virtual machines, all this crazy stuff. They did that first, and they're doing all that confidential computing, all that stuff first, which is great. They sell 1 or 2 or 3, maybe 5 machines a year. They're very expensive. They work really well, but that's where Linux is. That's where hardware is going in the future.
Okay.
It's kind of fun.
Okay. So if you want to facilitate this process, what do you do exactly? Like, do you invite them to a round table and say, like, guys, sit down here and discuss the API? Like, how does this process look like?
Well, usually it's like, hey, here's a patch. Here's a patch that adds this feature, right? And then usually we don't want to see a new API being added until you have at least 3 users, ideally, because 2 kind of means it works. 3 is like the magic number that, okay, this is really going to work. If other people don't show up and want to contribute, okay, we'll take the 1. Accelerator drivers for GPUs and other types of accelerators famously have been written in a way that are very specific to the hardware. So if I want to talk to that accelerator driver, I can only talk to it one way. And that's a hard problem. So they're trying to now commonize and form a common standard for the accelerator drivers. But the old ones got grandfathered in. So a new one might have to do a little extra work to make work with the standard thing. But there's just show up with the code and on the mailing list, submit it. And then sometimes, again, we have conferences all around the world. Like we have one in Europe, one in North America, one in Japan every year. Go to one of those, and we all are public there. And if you want to actually talk to people, or otherwise just, email. Email works great. Email works really good for technical discussions, especially when English is not your native language, because you can think about it, you can sit there and you can review it, and then respond. You can translate. As someone who lives in a country where my native language is not the native language, I really appreciate that. If I get a email in a different language, I can sit there, okay, I can read that, I can translate that, and I can write it back and take the time. It's not a, you don't have to do face-to-face or IRC chat or anything like that, which is, for technical stuff, is very good. So we're much more open to people from any background, which is good.
Okay.
And you can argue things technically in an email much better.
Yeah, this is very interesting. Like, I've seen a couple of like never-ending email threads, especially the heated ones. They are always the most public from the Linux contributors and maintainers. And how do you see this as a process of like figuring out some issues? Like, do you think, like, in a company, it would be wild to have this process public, like
right? I always say that.
This is
I always say, engineer, would you want your engineers' mailing list public? They're like, no. I'm like, okay. How about your manager's email public? No. We do that. We do it in public, right? The heated ones are kind of more fun, is we know each other. We've all known each other. So I used to say it as like, we're professional basketball players, right? You can yell at us like, oh, you stupid idiot, why'd you do that? Like, oh yeah, I shouldn't have done that. But because we know each other, we've interacted with each other for decades, right? But you don't do that for a child's basketball game, right? Kindergarten, right? You don't yell at them for that. It's a different model, but we're in public, so we do have better decorum, and we have changed our ways over time, because we should be accepting and open for everybody, and we shouldn't curse. We can curse code, don't curse people, right? And complain. Yeah. So critique code and argue that. And that's the key. And sometimes we don't agree, right? Sometimes we don't agree on things, and that's when things get hard. Sometimes we'll sit down and we'll call up and like, okay, let's talk. Or we'll say, hey, we'll meet in person and hash this out. Some things are harder to do that way. So we do. I mean, I've been in meetings, some of these conferences. There was the plumbers conference that happens every year. Is there for us not to give presentations, for us to get in a room about specific topics and hash it out. Famously, one of them was, there was one slide that was given. It says, the doors are locked. No one's leaving till we agree. It's like, okay. Doors weren't locked. It was fine. And we did. We finally, okay, let's argue this out, and we figured this out, and we're professional enough. So some things it seems like it takes longer because it might take us 6 months to get to an actual meeting, but we can hash it out and figure it out. We're human. We'll get there.
Okay.
And we'll argue about the patches. And sometimes the worst part is when you have to break a tie, right? You don't want to have to break two people's argument, right? And that's what comes down to the maintainers and their decision. And that's the hard part. You don't ever want to have to do that, right?
Okay. What were the heated ones? What were the ones that you remember from the past? What was like there was a lot of conflict and it needed to be hashed out in a room physically?
Disagreements about how we should do some power management issues. It's like, oh, I agree. I think it should be done this way. I think it should be done that way. Things like that. Or you're coming up with a new locking scheme. Android famously came up with a new, different way of doing locking for embedded devices that the embedded people didn't like. Those people, we had to get everybody in a room together and figure out, okay, I know your use case is actually different than my use case. So let's figure out how this is all going to work in a different way. From a technical point of view, and we all worked through it. And it turns out the solution is a third one that works better for everybody. So it's usually it's not pretty watching it happen, but the results are pretty nice, or work out pretty well. And it succeeds over time. It's like engineering. It's creating anything. It's just humans, right? That's how we make stuff.
Okay. So
we just happen to do it in public. Most people don't do it in public.
Yeah, and that's wild. That's wild that all of this is happening in public. Well, have you thought about making at least some of it private, or is it a sort of like a source of pride that this is in public and you also stick to it? And
well, it turns out you create a better thing, a product in the end. So one kernel developer famously said, I was terrified the first time I started contributing to the kernel, not from a technical point of view, just because my name is now on that in a public view, right? Everybody can see that. And I can see I got it wrong. And so I spend the time and effort and energy to do it right? Because your name is on that. You cannot do it as anonymously. You do it, and it's proven. There's been research on this. If you can just check code into a repo behind a firewall, you do a lot less. You do a lot worse work. Look how long it takes companies when they want to open source a product or open source some code. They have to go and scrub it all and clean it up and make it better, right? Well, why didn't you do that in the first place? Right? So we require that in the first place done. So you end up with a better product. It's a better software a better solution from an engineering point of view to do this work in public. It's just because you take more pride in it. Your name is on there. You can go back and see all the mistakes I've done in the past, which I've done a lot, but I've done a lot of other good stuff too, and everybody has. But we're human, right? As long as we fix our problems, all is good.
Okay. Oh, can we talk a little bit about maintaining compatibility with the new stuff? Like, this seems to me, I've worked on a library that was used internally in a company, and it was like to remember, and like it was like Scala, and then Scala needed to be binary compatible with the Java stuff. So like even if you add a new parameter that has a default argument, it's not binary compatible because it would be underneath like a different Java. Like all these compatibility issues, to think about them, to remember them, like it's horrible. And then like to do this in C on such a large scale project, I can't imagine what is this to do that. So
well, remember, so our API that we keep stable, compatible, is very small, right? It's our user to kernel boundary. The boundary within the kernel, we refactor the hell out of all the time.
Oh,
I can go and change it. Like I'm changing some APIs right now internally, and I can go back, and the goal is to change them in a way that the compiler catches the change, so that I can go through, and if I break the build, I didn't do it right? I don't want to make a change that I don't break the build. So break the build, and then I can fix it all up properly. That's the goal. And so internally, we want to be able to refactor and rewrite things. That way we can make things smaller. We can make things better. But that layer between user and kernel, we have to keep solid. We have some tricks about how to make that work. We have some rules on how to do that. We have a whole document that says, if you're going to write this API, here's the things to think about ahead of time that we messed up on. Don't do this again. Like padding. Yeah, do you want to do padding? No, you don't want to do padding. If you are going to have extra padding, always check that it's 0, right? Because if you come up with a new field in that area, you're going to set it to something. Well, if I never checked it in the first place, how do I know you're not using the old API? Things like that. Octal numbers. And sometimes you look, and sometimes we just give up and we make a new system call. We're like, okay, I want to. There's read and read 2 and read 3. There isn't read 3, but it's the same idea. We just go on and do new system calls. We can do new system calls. But that API, that boundary there is very small. There is some gray, fuzzy area because we do have some virtual file systems that you can see what the device tree looks like in your system in proc and sysfs. Goal of those is to make additions and changes over time that do not break. And that was the goal we learned from the proc file system. So we made sysfs to be future compatible. There's some pretty simple rules about how to do that, but it's tricky. But C makes it easy. That layer between user and kernel space is binary compatible in a very, very simple way. We don't have to worry about lots of nasty padding rules and things like that. So it's okay. We have it much easier than libraries. But that being said, it's a good engineering practice to do this, right? You don't want to break your users. You don't want to do that stuff. Now, famously in the very beginning, we used to break things. Now we've learned that's not a good idea. But that's our one rule. Our one rule of kernel development is you don't break user space on purpose. And that's when you'll see the biggest flames, when somebody says, no, I have to break this. And then Linus or other people will say, no, you cannot break this. Sometimes, famously, we will watch, there were some machines, I was like, okay, I know Andrew's running that old machine, and when that thing finally goes out of commission, then I can change it because nobody else is using that. So I can finally do that. Sometimes we watch that. And sometimes we're like, please unplug that architecture. I know there's only 2 of those boxes in the world. If you just unplug it, then you can fix up so many nice things. Things like that. But yeah, it's an engineering task, right? And API design is hard. It's a tough skill.
Yeah. And okay. It's a weird question because like you mentioned that a lot of the development is reactive. Like there are things that need to happen because it's in the interest of somebody. So somebody comes with a change list and wants to merge something. How in this process there is room for innovation? Like imagine that you want to do, or maybe is there a place for innovation, like rewriting or making a new way of managing virtual memory, for example? Like how in this, is there a place to do things for Linux to sort of innovate on the systems of like kernel design or stuff like that? Or is it more like people adding patches and patches and patches, and at some point, like, is there someone who says, it seems like we started out in this way, now we're kind of here, so maybe we should like rewrite this entire thing to reflect the new changes?
Both. We do both. So when you submit a patch to the kernel, you don't get the chance to, I am going to replace this big thing with this other big thing, right? That's not going to be. You have to break your work down. Like your old math professor said, show your work. Show me each little tiny individual step along the way as how you're going to get there. So way we do kernel development is traditionally like, okay, I want to do something new. You hack it up to pieces. You have an end result. Great. Then you start back at the beginning. How do I get to that end result from this point in time? And I build steps all along the way. And then you submit them for review all along the way. And what usually happens is about a third or halfway along the way, people change things and suggest things and modify things and say, oh, why don't you do that this way, or other stuff, that your end result ends up being better than what you first ended up with. And so that's a really cool way to watch our engineering process at work. Famously, like I did the driver core model, me and another developer. And as we were doing that, some other people, we wanted to just drop it in, like, no, break it up. And, oh, can't you do this other stuff? And we ended up creating something that everybody's like, oh, I can use that over here. And we can split that up even more. And the end result was so much more better and flexible and powerful than anything that we had ever come up with in the beginning. So it's cool to watch that happen. That being said, yes, sometimes we do pile patches on top of patches on top of patches. And it's like, okay, let's go back and rewrite that. And famously, it's hard to get companies to sponsor that work, right? Because they want to add their new feature,
Yeah,
right?
exactly.
So Thomas Fleixner and other people have been like, they had to refactor the kernel a lot to make real-time Linux work. It's a 20-year process. Linux can run in hard real-time systems now. A lot of stuff had to be changed and refactored and stuffed in order to make that happen. And that work was sponsored, but now that's done, but there's still other areas of the kernel that, oh, nobody's touched that layer in for forever. Maybe we should look into that, or maybe we shouldn't, and things like that. The fun thing is to watch when people replace things at the bottom and nobody notices. Linus rewrote some core locking primitives a while ago. He rewrote locks. I mean, I talked to some Microsoft engineers like, there's no way we'd ever be allowed to be even able to do that. But he rewrote them, and because new processors came out and things worked better, and he did that, right? Nobody noticed. So you can rewrite things at the core levels. In a security update, Linus rewrote the path from user space to kernel space. That syscall layer, the one that everybody uses, he rewrote that. Nobody noticed because of some security issues that we had to deal with the hardware. That was rewritten on the fly. Nobody really noticed that, and that layer was done. So our goal as an engineer is every single change that goes into the kernel can't break. You cannot break the build, you can't break the functionality. So everything you have to submit has to keep working. It's more engineering effort to do that. We waste engineers' time at the expense of maintainers' time because it's easier to review that. If you send me 20 patches for a change, I can go, oh, great. Well, first 5 are fine. They're obviously right. I'll take those. And then you take the rest and you refactor and you go again, and you go again, and you go again. You can whittle away at the problem. And that's a good thing to do, but it takes some extra effort and time to get there. It's hard. It's a hard task. So we have both things happening at the same time. And it's a moving apparatus. Again, 9 to 10 changes an hour, 24 hours a day, 7 days a week. That's insane rate of change. I talked to other kernel developers, other operating systems. They're like, you were going faster than us so many years ago. There's no way we can keep up. It's fine. It's just cool.
Okay. Can we talk a little bit about this process? How does it happen so that the stuff is changed so often, and talk a little bit about the release cycle and the development process of people wanting to add change lists to the kernel?
Sure. So you send a change in email, right? It comes in an email, has to do one thing. You have a little description at the top. Say, this says this, here's the patch, and I'll review it. You send it off, we have tools that say, if you change this part of the kernel, here's the people in the public mailing list you need to send it to. Send it off to them, they read it, they review it, and then they add it to, the maintainer will take it and add it to their tree. So I maintain USB. So I'll add it to my USB tree. All the subsystem trees, we have about, I want to say 700 of them, maybe 600 of them, get pulled in together every day into one big tree as a merge. So somebody merges them all together to see where the conflicts are and see what happened and what broke and if things happened, and then they'll report back to us. That's cool. That's a good merge of all these things together, and we see that happening. And we all work on this. So we have a development cycle that's about 2.5 to 3 months. I don't know how many weeks it is. And we've been doing for 15 years, like clockwork, doing a release. So say the point of time starts, so Linus does a release. So then we have 2 weeks in which the maintainers can take the stuff that's in their trees and send it to Linus. All new features, all new stuff that's been sitting in our trees for up to then. We send it to Linus. He doesn't pull directly. We have to send it to him individually. He doesn't pull from that tree that everything got merged together. That was just a staging. That was a little next tree, because sometimes things don't work, right? It's up to the maintainers to send stuff to Linus when they want to. So we have a 2-week window. We can add all sorts of new features. Tons and tons of stuff goes in there. And then he says, stop. We'll do release candidate 1. And then he does new release candidates every week on Sunday. And then from that point on, it's bug fixes only, or regressions. Regression to bug. And then if you want to add new device IDs for things, you can add new device IDs. Simple stuff. For bug fixes only for the next 7 weeks. And then new release comes out because it all looks good. We start the cycle over again. So during that 7-week cycle, people are still sending new features. So it's up to the maintainers to take those and add them to their local trees that are tested and waited for the next release cycle. That's it. So it's a bundling things up and going. It's a time-based release process. And it's a short time-based release process, which is good because that means if you're trying to get a feature in, I want you to get that feature in, right? Just by virtue of that. But I don't want to take something that isn't ready. So if I don't think it's ready yet, I can say, wait a release cycle. Let's do another version, figure this out better. Let's not take it now and fix it up later. Get it right. Because you're like, oh, okay, 7 weeks, 8 weeks, I can do that. I can get my release cycle out there. You don't have this gating of like, oh, it's only a release every 6 months. You don't have to worry about that. So time-based release schedule is good. So Linus does a new release and the whole process starts over again. That's Linus's development cycle and the whole maintainer cycle. That's Linus's release. Now, Linus's releases are great, but it turns out you want to make a product, right? You don't want to. What happens if week 1 after a release happens, there's a bug found, right? You want to get that bug in you don't want to wait 8 weeks for that. So I take that and I make the stable releases. So I maintain the stable releases. So I take Linus's release and then I start adding patches to the stable releases for fixes that are in Linus's tree. So a fix goes in the Linus tree, then I can take in the stable release. And I'll send you a little picture of how the graph breaks down. So then I do release every week of the stable releases, and I keep multiple releases going, branches are going at once. And then that's what you pull for, and that's what you put in a product. So bug fixes go into our stable releases only if they're in Linus's tree first. And that's a hard and fast rule. Almost always. And that's a really good rule because if you have a regression, you want to fix it you don't want to have to figure out, oh, I fixed it in a stable release, but I forgot to fix it in Linus's tree. And then we keep on going. And we do releases like that and been doing that for 18 years.
So Linus tree is like the most up-to-date version from which you pull and update the bug fixes to stable?
Yes.
Okay.
Yep.
Okay.
So the bug fixes flow into stable, and when you send a patches the bug fix as a maintainer, you can tag them saying copy stable. So it'll automatically, I'll see it and I'll flow it into my tree. A lot of people forget to do that. So we have some bunch of tools that scrape the tree and see, oh, this does look like a bug fix, and we'll add it too. But yeah.
Okay.
So 10 changes an hour going to Linus's tree. About 35 changes a day are going into the stable trees. So that's quite a reduction. And then out of those 35 patches, 13 of those end up getting a CVE. So we do 13 CVEs a day.
What?
Yeah, that's our rate of change. So we go from 10 changes an hour, 30 to 40 changes stable a day. 13 of those end up being a CVE.
How much time do you need to make a release?
A release for Linus's release or my release? What do you mean?
When you say this, you're making a stable release, right? Like how much time does it take to actually build and compile everything?
So I mean, it takes 3 minutes to build a release on my machine. But I'll put out a release candidate for here's a stable release, all these patches and in there. Go test it. So a bunch of people test them. I give them 2 days, 3 days to test them. And if anybody reports problems, I'll fix them or drop patches usually. And then I'll do a release. I did some earlier today. I did a bunch of releases. I can just push a button and it cranks out a release.
Okay.
It's all scripted.
Okay. It's so weird to think about a 40 million line of code project and also like this rate of change and this many releases and everything building in 3 minutes, and like it's difficult to wrap my head around it. Like it's
just simple code. It's just grown over the years, and it's nothing complex here. It's just patches moving through email.
Okay. So can we talk a little bit about Linux Foundation? How does it work that there are only 3 people developers there? What's the goal? You mentioned some of the trade company and like letting other companies talk in terms of APIs, but generally speaking, Linux Foundation also sponsors a whole lot of other projects apart from Linux. So maybe we can talk a little bit about it.
Well, when it started out, it was OSDL, which came before that. We needed a neutral place for companies to be able to talk and work on projects together, as well as a place that can do our marketing and do our legal stuff and handle things like that. So all open source projects need a foundation to handle the legal bits and pieces for it. And nobody wanted Linus to go work for a different company. So Linus is like, I'll go work for a neutral place. So Linus worked for the Linux Foundation. And then Linux Foundation over time realized that this model of working in open source projects, and they had a really good marketing people, some really good legal people, can work for other open source projects. These companies that were contributing to Linux were also contributing other open source projects. So they're like, hey, Linux Foundation, can you host these as well? They said, sure. So over the years, Linux Foundation has hosted more and more open source projects in a vendor neutral way. And that's really cool. So they run conferences, and the conferences they run are really good because we're not making a profit. All the money for the conference goes back into the conference. So it's cool. So it's not a profit making company for that. There's a lot of people working for the Linux Foundation now because a lot of conferences happen and a lot of projects are there. So a lot of other projects that go to the Linux Foundation will come and they need some IT people, or they need a project manager. So Linux Foundation can hire that and work on the project manager to do that in a vendor neutral way. And they do that. And Linux Foundation also has other projects like OpenSSF that helps out with security of open source projects. There's some good people working there. There's a marketing department. There's a research department to do open source research and put out papers for companies. The legal department helps us out a lot. I don't think people realize how much you need a good legal department, right? So handle the patent issues, handle the trademark issues. The trademark group at the Linux Foundation just got an award for how well they've done by other trademark attorneys. So they're actually really, really good attorneys that handle trademarks, because you want to make sure that nobody infringes on your open source trademark, right? If you you could put out source code and say, I'm Linux. It's like, well, no, you're not really. Right? So we have Linux Foundation has trademarks, right? So there's three of us, Linus, me, and Shuakan, who work for the Linux Foundation in a vendor neutral way. So our contracts are such that we can't tell them what to do and they can't tell us what to do, which is great. But we can listen. We both listen both ways. So we help. So I can work in a vendor neutral way and talk to companies in a way that is not representing any single company. Shua can do that as well, and Linus can do that as well. And that's a very powerful thing. Shua also runs the mentorship program. We have a lot of interns come through, and the companies sponsor the mentorship program, and they go through and for Linux kernel or for other projects as well, can have a mentorship program, and they get jobs. And most of them get jobs and disappear into companies, which is great. Good job. So they do good work like that way. So it's a trade organization, handle legal stuff, handle trademark stuff. And marketing. You kind of need somebody when a press wants to call up and ask about some questions about Linux. Well, they can call the marketing people and they can get a hold of us in a proper way. They know how to answer the questions properly. And it's important. When we didn't have this, it was a real problem, right? We had real issues. We had legal issues. We had marketing issues. We had conference issues. So if we didn't have the Linux Foundation, we would need to have something like the Linux Foundation. So at the core, it's Linux. And as proof of this, the Linux kernel community has an elected representative. So we elect people to the technical advisory board every year. There are 10 people on the technical advisory board, and the head of the technical advisory board sits on the board of directors of the Linux Foundation. And we're the only project that the Linux Foundation manages that does that. So the Linux kernel community is directly represented at the board level of the Linux Foundation. And that is a representative from the Linux kernel community themselves, right? These are developers there representing that to make sure the Linux Foundation is still doing things good with Linux. Like I went to the Cloud Native conference in London a couple of months ago, and there was like 12,000 people. And I was there to give a talk saying, hey, you guys are all still running on top of Linux, So there's Linux underneath this stuff, but they don't realize that. But Cloud Native, I mean, there's Kubernetes, there's tons and tons of companies working on that stuff, which is great. And that's fantastic and wonderful. But Linux Foundation does do more. Too.
Okay. It does seem a little bit like you, Linus, and Shiwa Khan are irreplaceable. Like, if you were gone, there were so many companies that have vested interest in developing stuff, right? And they are, in a way, sponsoring the work on Linux, right? But the other hand, there are only 3 people involved in, let's say, running the show from this perspective. So is there, first of all, is this enough, like 3 people to handle this stuff? And then do you have some plans to grow that? Like, how do you view this framework. Is this enough?
Well, we're not irreplaceable. I'm not going to say that by any means. We do work, but there's 700 maintainers, right? Maintainers of these different subsystems in different parts of the kernel work for different companies, right? So these are all individual developers. Most all subsystems now have shared maintainership. So multiple people working on the maintainership together. The networking maintainer, when the core networking maintainers had a stroke a number of years ago, and he's better now, but there was 2 maintainers working on it so they could share the load, and Jacob took a load and helped out. Now David's better. But so we have shared maintainership for a lot of stuff. So while Linus and Shua and I are great and we do happy about what we do, there are other people doing this work too and helping us out. I'm not the only person doing these stable releases. I have somebody else helping me. Sasha helps me out a lot. The CVE team that we do CVEs, there's 3 of us that do that work. So Linus does releases when Linus couldn't do that. I did releases for him. So Linus has multiple people that can write to his repo. I have multiple people that can write to my repos. Our repos are all public or you can clone them instantly and take that. So we have ways of working around that. So we're not irreplaceable. I like to think we do a good job, but it's we have a lot of help. So there's a lot. There's 4,000 of us a year, right? It's not just 3 of us by any means.
Yeah. Okay. So how does then Linux Foundation receives money from the companies? Like companies on one hand sponsor the project in terms of like their own developers work on Linux, right? But they also sponsor like financially the Linux Foundation and with that like conferences, events like that. Is this a good view? Or not?
Yeah. Well, conferences are independent. So conferences run themselves, right? They have sponsorship for conferences.
Okay.
Right. But to be on the board of the Linux Foundation or be a member as a company, yes, you do pay. They're pretty cheap. It's not that much. Dues are only good for once a year. So if you don't like what they're doing, you don't have to pay them next year. It's very transparent if you're on the board, what the money goes to. It pays for legal fees, pays for the marketing fees, pays for the IT. We have hosting issues as well, right? It pays for that. It pays for me and Shua and Linus and other people. There's some overhead. When you join for company-wise, there's companies fund a project manager, right? So you want to work together on it. If the Linux Foundation hosts your project, there's some fees to have it host your project because you need to pay for that project manager and that IT group and the bandwidth, right? So there's a tiny cut that comes out of that. So it's not a huge profit, right? It's not a profit. It's a non-profit company, right? So it's not like we're in it. There's no stock. Like my wife reminds me every once in a while, like, "Hey, you're not getting any stock." I'm like, "Yeah, I know I don't get any stock. I work for a non-profit." That being said, it's a model that if people didn't like, they wouldn't keep sponsoring it, right? Because nothing's keeping them from doing that. So they feel that like they're getting value from this. And over the years, we've had big problems that we've had to solve. Only way we could solve it was through the Linux Foundation. Secure boot was coming down. The only way we could solve that was through the fact that the Linux Foundation could handle the legal resources. We could handle the vendor neutral resources. We had the vendor contacts that we could use and get that solved in a way that would work for everybody. And that was a good example of how that worked out.
Okay. All right. So looking into the future, what do you see on the horizon for Linux? Like, I know that you mentioned that there's a lot of the development is kind of reactive, but is there a direction or that you see where Linux is heading? Like, what do you envision Linux to be in terms of like operating system share, or like what do you see when you look into the future? Or you don't, or maybe you don't think at all about the future.
Well, we don't think about the future. We want to make sure I want to see Linux succeed, right? So my goal is to make sure Linux works well for you and your use case, right? Because it turns out everybody has the same use case, as I said before. So I want to make sure that happens. So I talk to lots of companies, lots of developers, lots of users about what problems do you have? How can we solve the problems that you have? And let's make that easier. How do I get you involved so that you can contribute easy? I do a lot of education on how to contribute to the kernel, how to get involved. I work a lot with new people, a lot with interns in order to get involved. Because once you start getting involved and have a buy-in, then we grew our community, right? We want to make sure we continue to grow and continue to succeed that way. So that's my goal, right? And that's the goal of Linux overall. We want to make sure it still works as a solution for you and your problems. And that's it. So, but in order to do that, we have to react to the problems that people have. So we have to talk to the people, right? So we don't know what the problems are. We kind of know what the problems are for the next maybe 2 or 3 months, maybe 6 months out, depending on what they are. And we go from there. Look at our conferences and see people have talks about, hey, look at this problem over here, or we need to solve this over here, or here's this new feature. How do we do this? And we go from there. And it's reactive that way, which is kind of fun. It's a real world use, right? It's not a theoretical, I wonder if we did this, would it be good? In the very beginning, we had we needed to catch up to Unix, right? We had to be feature parity. We had to solve all these problems that other operating systems have. And then we did that. And then we went past them. And I mean, I was at a conference once with a bunch of other operating system people. I was like, how'd you solve this problem? They're like, what problem? I'm like, oh, you haven't hit that yet. Oh, no. What about this? I was like, no, we haven't done that either. I was like, oh, great. I'm on our own. How are we going to solve this problem? And it's always easier to copy other people, right? It's harder to do stuff on your own. And we've been on that on your own path for quite a while now. And so we just react to new hardware types, react to new specifications coming out, react to new workloads. I mean, I don't think the hardware vendors are ever going to stop making new chips, right? If they do, then then we'll slow down. But until then, let's just keep on going. It's kind of fun. It's fun. It's fun that way. It's new stuff all the time. It keeps things interesting.
A lot of the viewers of this show are involved in game development, so they're very much celebrating Steam Deck and Linux running
Steam
there.
Deck is amazing. I love that thing.
So tell me about, like, from your perspective, was there like a lot of work involved into making sure like Linux as a kernel is able to be on Steam Deck, or how does it work from your end?
So my end, I don't see much. So Steam Deck is, I've known the Valve guys, people, for years. I had one of the first Steam boxes, and I lived in Seattle for a long time, so I would go visit them. They do great stuff, and the idea is wonderful, and it's an open distribution, and now it's on under multiple hardware. They did an amazing thing by getting Wine and Windows to work on applications to work on Linux. It's an amazing technical feat. That being said, I see the pieces that I see a lot of work by AMD and some contractors that Valve also pays to get that hardware working really well. And because that's an AMD chipset in there, there's a lot of issues. Like they test all my stable releases on the Steam Deck to make sure it continues to work well. There's also some changes to the kernel we made. Recently, we added some code and an API layer to emulate some Windows locks. So ways Windows does some locking model is different the way than POSIX and Linux does locking model. And Wine was emulating this in user space for years. And it turns out if you put it in the kernel, it can go faster because the kernel can see across those processes, right? We can do some things that you couldn't do. They submitted some changes to us, and we had some core locking people look at it and review it, and scheduler people look at it and review it and make some suggestions and changes, and it's merged. So newer kernel versions now will actually run Windows games better because of that. So less overhead and more frames per second. There's some really cool stuff happening with the scheduler model. I was just at an embedded Linux conference last week, and they showed some, you can run a scheduler model that's specially tuned for games. And they showed a workload of walking through the game, the traditional scheduler model, and you switch it to a different one, and the frame rate just instantly goes up. And even if you have a workload on the machine, frame rate is up there, and it's just smooth and silk, and it works wonderful. So there's a different model of, you can write a scheduler in different ways that'll work better for games. And now you can do that in user space in eBPF model to inject your scheduler model into the kernel, and away you go. So that's a really cool feature, and I think that'll be coming to more Steam games. There's a whole modder community out there that are doing amazing fun things with that stuff, and it's great to see. So yeah, I love it. I think it's an amazing product. It's a fun thing to use. I have the thing. I bought the new one as well. It's great. And then you can run Steam on your laptop as well, and your little other laptop or your desktop.
Yeah,
it works good.
Do you play video games?
Occasionally, yeah, I do. I use the Steam Deck a lot. Play Factor.io on my regular time.
Oh, nice.
Yeah,
nice.
Some fun little games on Steam Deck I use. Nothing, no AAA games.
Okay. how does the Gen AI tools now impact the world of Linux development?
You mean advanced pattern matching or applied statistics? Not at all. So the kernel is a pipe. So our job for the AI people is to get out of the way and let them run their workload through to the GPU and get it back out, right? So that's what the GPU drivers and the kernel used to do all the time anyway. For games, it just happens to work well for AI stuff. So from our viewpoint, it's just yet another driver. They use the existing kernel drivers and away they go. And we don't actually hear very much from them at all because they're just a server. Servers are very simple machines. You got a disk, a network, maybe even not even a disk, network, GPU, and away you go. So that kind of stuff is not affecting us at all. We've been using this type of logic for years to pick patches out for stable kernels. So we wrote some people, a professor and Sasha also wrote some papers years ago about how to, because we have a huge history of kernel of changes, right? So we have a body of patches that maintainers have said these are bug fixes, and then we have a whole body of patches that people didn't say that. Well, use this as the pattern to match this, and turns out it's very common and it works out well. So we find a lot of things that, and Sasha runs this tool on this tree all the time, and it's like, oh yeah, I miss them sometimes. Like, yeah, that was a bug fix. I should have marked that for the stable stuff. So we use these tools in order to make our development process easier that way, to pick out the things that we messed up on. And that's about it as far as Gen AI goes. And sure, they've trained all their models on our code base. It's 40 million lines of code, but
yeah, that's a great resource, probably.
Yeah, sure, fine. If you want to write another operating system, that's good. You will note that Microsoft never let the public models train on their code. So
yes,
that's fun. But no, yeah, I mean, so again, we get out of the way and away it runs. But all the workloads, they're all running on Linux, which is great. We're happy.
Okay. A lot of people on this show, from often game dev background, have this idea that software is in the state of decline now. And I wanted to ask you, like, you're coming at this from a different point of view, but you still use web browsers and like editors, various editors and stuff like that. So would you agree with this statement, or would you say it's a wrong one?
Well, we all long for the days that we learned when we were 12, right? I mean, that's the golden age, right? So yeah, I have to control my full machine, and only if I could do that then. So in the kernel, we're more complex than we used to be, right? We're more complex because the world is more complex. We have to solve a different problem. We have to solve a different threat model. We have to care about validating user input, right? Because we're used in different ways. This is a good problem to have. It means people are using our work. You can write some very simple code that nobody uses, and that's fine because nobody cares about that, right? If you're writing real world code that has to work with real people and solve real problems, yes, it's going to be complex, and yes, it's going to be interesting because the world is complex and we have different models and whatnot, but we can get that code out to zillions of different people. The web browsers, I mean, it solved a problem that everybody wanted to write once and use everywhere, right? Well, the web browser kind of solved that problem, and that's great. And that opened us up to more people being able to use our stuff. Yes, maybe sometimes the layers and the thunking is too big. I will note that in Rust, I was like, okay, I'm only pull in 4 libraries. And then I watched that expand to 200. I'm like, oh, what just happened? So then I go through and okay, I'm going to write this down and peel it back and peel it back and peel it back. And sometimes dependency trees are probably too big, but those dependency trees are there to help us solve a problem. I mean, we don't add them willy-nilly, right? And you can also go the other way. Look at the editor Microsoft just released the other day. People complain that it re-implemented a bunch of stuff in Rust that are in the libraries, but it didn't depend on any libraries. They did it all. It's very, very tiny. It's cool. So you can still, if you want to write raw code, write raw code. If you want to look at the Celeste developers, they write their own engines, right? They just posted a blog post the other day saying, well, this is why I write my own game engine, because I want to have control over this and I want to work on this type of stuff. Cool, why not? But people who don't know how to write game engines can grab Unreal or other things and make a game because they know how to tell a story. And that's a different skill, right? And how to tell a story. The number of us that can tell a good story for a good game and write a game engine are a lot smaller, right? Yeah. So, no, I can't do that. So I might be able to write a game engine. I can't tell a good story that way. So these layers of complexity make it such that it levels the playing field that more people can do things that weren't able to do things before. And I think that's a good thing overall. And you can peel it back. There's still demo scenes out there for writing JavaScript in like 2K, right? Look at the Pico 8 thing, right? I've written Pico 8 grade game code, and that's some amazing fun stuff. You have a self-contained little thing. The Pocket, little game thing that came out from, is it Pocket, I think? Or Panic made that little Pocket thing. That was a cool...
with the crank,
yeah.
with the crank.
There's a good resource constrained system.
It's Playdate.
Playdate, sorry.
Playdate, yeah.
Yeah, I have one around here somewhere. That's fun. I mean, that's a fun thing to play with, and it's a fun resource constrained stuff. So and people were making money writing games for that, right? That's cool. So if you do what you want to do, right? And yes, maybe you don't have to grab the latest JavaScript framework to do what you want to do, but maybe it lets you solve the problem faster. Great, because you want to go do something else. I mean, think about how things used to be before we didn't have free servers. I mean, you had to go buy a bunch of Sun servers and spin up a bunch of stuff in order just to make a company to have a website, right? And you don't have to do that. You can go rent a cloud machine for $5 a month, right?
Yes. All right.
And hardware's complex. I mean, hardware's gotten complex for reasons. So you can go back to run that old hardware if you really want, but that old hardware actually usually takes more power than the new hardware.
Yeah. Okay. All right. So I'm assuming you're staying optimistic.
I'm a programmer. If I wasn't optimistic, I would not be doing this job. Because it's like I see it. But the funny thing is, I see the bugs every day, right? I see all the bugs. I'm like, how is this working, right? How is anybody using Linux? I see all the problems with it. And my daughter, who's now a doctor, said, so like, it's the same thing with medicine. Like, all you see is all these people with all these problems. Everybody's sick all the time, but you never see the healthy people, right? You don't see the people that are doing just fine. I don't see the systems that are running just fine and nobody's having problems with. So it's the same idea, right? You know, yes, there are things that need to be fixed and going, and I'll work to fix that. But the fact that there's 6 billion Android devices out there running Linux is pretty amazing. And how many hundreds of millions of Linux systems out there? Yeah, it's pretty good.
Awesome. Greg, thank you so much. This was super cool. Thank you so much. And yeah, let's hope for Linux taking over a couple of billion of other Android devices as well in the near future.
It'll be fun. That's good.
Thanks a lot.
Thank you for having me. It was great.